Well, in the next 10 lectures, I will be talking about Markov chain, mixing times and graphs, and how we can use it on finding some sparse cuts or many sparse cuts, or even use it for k-cuts. And the references that I will be using for this series of lectures will be mainly about the two great books of Yuval Perez, very great books. So 2 books here, and you should also read 2 books of R.K. Chung, Fan Chung. One of them is in 1997 about spectral graph theory. The other one is 2006 book on complex graphs and networks. I also talk about the work of David Aldous. He's great. He's very great in these things, especially concentration of measures, as I remember. So also I will talk about Lapchi Lau and his student in Hong Kong University, and also, of course, Lapchi Lau has worked on Lowas-Simonovitz curve that I will talk about it. It's very important things. And even Fan Chung has talked about it a lot in his papers. And also, I will talk about Martin Dyer, and also people like Russ Bobley, Percy Diaconis, and many other references that I needed to give you very beautiful examples about Markov chains and graphs and sparse cuts. So we are at X, and so the transition probability depends only. So when I say this means that it depends only on X. And as usual, X0, X1 is a Markov chain, and the probability of xt plus 1 equal to y condition on ht minus 1, xt equal to x. I use the same thing as is written in the book of Markov chains of Yuval Perez. So this is equal to xt plus 1 condition on xt. And we usually say it is pxy. It has Markov property. And of course, ht minus 1 is the set of events that ht minus 1 is the intersection of all these events. And so the transition matrix, this is a probability matrix. So the number of vertices times the number of vertices. So this is big. And my motivation, I have done many research on Markov chain, but I use it for dynamical systems. I used to work on dynamical systems many years ago, about 15 years ago, when I was working on nonlinear control theory. And there we had some attractors, some dynamical systems, and so it behaves something like dynamical systems that after a long time it converges to the stationary distribution. And so in graphs is the same things. The graph is the discrete version. You can think of graphs as a discrete version of those dynamical systems. So for me, both of them are the same things. And every night you can, before you go to bed, you can create a new kind of Markov chain, either a new kind of random walk, anything that you like, because there are infinite ways that you can use. You can create new random walks, or in general, new Markov chains. There are many different ways to create it. And of course, you should check if it has good properties or not. You should check that if you can verify the transition probability very quickly. Otherwise, it may not be interesting. And so when P is stochastic, P of x and y is equal to 1. And let's talk about this. Let's review for those who are not familiar with these ideas. So mu t is 1 by n vector. So if you multiply it by mu t minus 1 times your transition matrix, which is n by n, this is 1 by n, so this is 1 by n. And for any initial distribution, mu t is equal to mu 0 p. So matrix p to the t for any t greater than or equal to 0. So when t goes to infinity, it gets closer and closer to stationary distribution, which we call it a limit distribution. And as you see, it's just the eigenvalue of 1, and this is the eigenvector. Pi is the eigenvector. So for different starting distributions, we can define P of mu and E of mu. Expectation, for example, given that mu 0 is mu is mu 0. And so in the t-step transition probability, t-step transition probability, P to the t, as I said, x and y. So this is just probability that xt, after time t, we are in the y state. And for notations, we always use, for example, mu of a is mu of x in set A. Also, the row of P indexed by x, we show it by this. This is the row. This is the row of P. So if chain has distribution mu at time t, then it has distribution mu p at time t plus 1. So at time t, it has distribution mu, and at time t plus 1, we have distribution mu times p. So these are very basic things that everybody knows. So we multiply column vector f by p from the left. So think of this as a function on a state space and the x entry of resulting vector. So pfx, its meaning is just pxy f of y for all y. And this is, you can write it as f of y p of x x1 equal to y, and this is expectation of f of x1. So we are at time t, and we go to time t plus 1, and x could go through, for example, x1 could be 3, x1 could be 2, x1 could be 1. It goes to different states. So I just want to skip random mapping representation because I will talk about it when we reach the coupling. So what are irreducible chain? Irreducible chains. Everything that I say has the corresponding equivalence in dynamical systems. For example, stable manifold, unstable manifold, center manifold. For example, if you want to find those points that, for example, x dot equal to f of x, when f of x is equal to 0, you can find the equilibrium points. And it can have many equilibrium points. So near different equilibrium points, it behaves differently. And this could create many complex motions, such as chaotic motions. And so in this context, you can think of it as dynamical systems. But in computer science, our concern is just graphs, and even either finite graph or infinite graph. So this is a very good framework to think about. And the future of computer science is related to Markov chain and mixing times, and creating very complex and new random walks and Markov chains. So irreducible chains is that if for any two states x and y, there exists at an integer t, possibly depending on x and y, such that p to the t of x and y is greater than 0. Because when it is 0, then, for example, in dynamical systems, you don't want to reach one equilibrium point and you cannot get out of it. So when you go inside this space, for example, locally this space, when you go inside this space, you cannot go out. It's like a black hole. So you don't like this reducible stuff. So this is reducible. We don't like it because we cannot do ergodic things and capture beautiful new states of your Markov chain. So for any two states x and y, there exists an integer such that pt x and y after time t, after t steps of your random walk or your Markov chain, you want the transition probability from x to y after t steps to be greater than 0. And it is possible to get from any state to any other state using only transitions of positive probability. And let's talk about random walks on graphs. As you know, this is for example, n cycle. And you go this way, this is clockwise with probability half. You go anti-clockwise with probability half. So it's n cycle. So if coin lands tails up, you move one step counterclockwise. If coin lands heads up, you move one step clockwise. And we can define a simple random walk on G to be a Markov chain to the state space V, and P of X, your transition probability, is 1 over degree of X. For example, this is X. The more we have such edges, for example, 1, 2, 3, 4, 5, 6, 7, 1 over 7, 1/7. So the probability gets closer and closer the more we add new edges. So it's 1 over degree of x if y is a neighbor of x. Otherwise, your probability is 0. And it's strong, the notion of stationary distribution, as I said, it's just PP. So long-term limiting distribution. We rewrite it elementwise. So whatever we do in linear algebra, you can do it element-wise. So that may look complex, but it's just element-wise interpretation of whatever you do in linear algebra. And so it's P of X and Y. So to get a probability, we simply normalize by degree of Y to be equal to 2 times number of edges. And from the probability measure, P of Y is degree of Y to 2 over degree of Y. So degree of Y, if you sum it over all vertices, so it becomes 2 over Y. This is very important. For example, a vector could be 2, 12, 3, 12, and 1, 12. And for example, we have 5 elements. This is just an example. And when we talk about heating times and first return times, it means that, for example, the heating time, tau of x, is by definition the minimum time that xt reaches x. It hits that. The minimum times that your random walk goes, and then hits a point x. The minimum time. It could start from there, it could start from there, the minimum time that goes here. But maybe this is the closest one. So the tau of x for this path could be this. So the minimum time that xt becomes x. This is the heating time. And why do we care about this? There is a proposition that says if tau of z is the probability of tau of z is less than infinity is equal to 1, then pi tilde satisfies pi tilde p equal to pi tilde. And also, if expectation of tau z is less than infinity, pi equal to pi tilde over ez expectation of tau z plus is a stationary distribution. That was not important. I want to talk about lazy random walk. I introduce it because we use it in for example, many things like Lowas-Seminovitz curve. We use it in many different constructions by different people, like Yuval Perez and many different people. So lazy random walk, it means stay at current node I with probability half and move to the neighbor uniformly at random with probability half. So I'm just recalling that pt plus 1 of I is the sum over all j's. ij is an edge. pt of j 1 over d of j. So if D is a diagonal matrix, such as D1 up to D of n, and D is a degree, and PT plus 1 is just AD minus, it's kind of normalized, and then times PT. So this becomes AD minus 1, T plus 1, P0. So if P is a stationary distribution, pi equal to AD minus 1 pi. So our transition probability that we talk is just AD minus 1. So pi is the eigenvector of AD minus 1. because 1 times pi is equal to transition times pi. And observe